Hello students, welcome back to Master Stroke KCET 2025 series, and today we are going to discuss the one shot for the chapter solutions. Okay, so this is going to be like complete lecture where I'll be covering all the important concepts, all the important formulas. So please sit with a notebook and a pen and write down all the important things that I'm going to discuss. Now this chapter is very easy and scoring. The only thing that you need to focus on is your calculation part. Okay, since there is no calculator in your KCET examination, so make sure that you do this question practice without calculator whenever you do it at your home. Okay, so that is an instruction. Let's get started with the first concept here. So what all things I'm going to cover in this chapter? Okay, so this is the entire thing that we are going to discuss in today's class. So first we will discuss the types of solutions, concentration terms and solubility. Okay, after that we'll come to vapor pressure, ideal and non-ideal solutions, and in the next part we will discuss about colligative properties and abnormal molar mass. Okay, so this is the entire thing that we are going to study in today's class. So please make a note of all these topics. Total 7 topics. First will be types of solutions, concentration terms, solubility, ideal and non-ideal solutions, vapor pressure, colligative properties and abnormal molar mass. Now coming to first here, weightage year wise, you can see for the last years it carries a very high weightage, 3 to 4 questions, but now since the number of chapters are less, I easily expect that this chapter can have a weightage of 5 to 6 questions at least. Okay, you can expect 5 to 6 questions in this particular chapter definitely, because it is a very high weightage and important topic. Now coming to the first thing, that is solutions and its types. So a solution consists of two things. One is your solute and the another one is your solvent, right? Solute and solvent. So the type of solution is based on the phase of the solvent. Means if the solvent is liquid, then it called liquid solution. If the solvent is gas, then gaseous solution. If the solvent is solid, then solid solution. Now here we have lot of examples, and this is a very big bank of question from where you can be asked, like any particular word will be given. For example, I'll take amalgam. Okay, so amalgam of mercury with sodium, which is the solvent here, which is the solute here. So that you should be knowing. It is a liquid and solid solution, gas in solid, solid in solid. So this is important both for your PU2 and for your KCET examination. Questions, similar questions have been asked in the past as well. So please make sure that you do all these examples properly. Okay. After that we have concentration terms. So these are the concentration terms that we have. 7 concentration terms are there: mass percentage, volume percentage, mass by volume, parts per million, mole fraction, molarity and molality. Okay, but these 3 are very, very important because we are going to use them regularly in the numericals. So you should be very thorough about these 3 concentration terms. Now coming to the first one, mass by percentage. What is that meaning? Mass of the solute by the total mass of the solution into 100. Okay, mass of the solute by the total mass of the solution into 100. This is your mass percentage. Now for example, 10% glucose is mentioned. That means what? 10 gram is solute, and here solute is glucose. Okay, now 100 gram is solution. Okay, 10 gram solute or 10 gram of glucose, then 100 gram of solution, then what I have? 90 gram of solvent. Okay, solvent means water, because here it is mentioned water by mass. So that is the meaning of this 10%. So whenever in numericals it is given 10% ammonia, 10% ethanoic acid. So you should know that 10 gram is ethanoic acid in 90 gram of water. Okay, this is very important. Next, coming to volume percentage, it is the same thing. Volume of the solution by the total volume of the solute by the total volume of the solution. Okay, so here if I have 10% of ethanol, then it means 10 ml of ethanol in 90 ml of water to make a total of 100 ml of solution. Okay, solute, solvent, solution. Similarly, I have next one, percentage of the component, mass of the component by the total volume of the component, total volume of the solution into 100. Okay, this is your mass by volume. You can see mass by volume. So mass of the solute by volume of the solution into 100. From the name only you can easily guess. So for example, here it is given. Okay, suppose I write, I'll give you a simple example. Suppose it is like 10 gram, okay, 10%, just a minute, or let me explain this example only. A liter of sea water which weighs 1030 gram contains about 6 into 10 to the power of minus 3 gram of the dissolved oxygen. Okay, such a small concentration is also, okay, I changed this one, one second. Okay, now we were in mass by volume, right? One second, mass by volume. So suppose I write here, that is, okay, 10% glucose, okay, W by V. So this means weight by volume. So that is the meaning here is 10 gram of glucose is there, okay. Then what is next? We have 100 ml of solution. Okay, we don't know anything about the mass of the solvent, that depends on the density, but 10 gram of glucose is present in 100 ml of solution. Clear? That is the meaning of W by V. Now next one we have is your parts per million, so next concentration term, parts per million, number of parts of the component by the total number of parts of all the components of the solution into 10 to the power of 6. Okay. Next we have here mole fraction, which is important, that is number of moles of the component divided by the total number of all the components in the solution. Okay, so if you have in a binary mixture moles of A and B are there and they are represented by Na and Nb, the mole fraction of A will be Na by Na plus Nb, and this is represented like this, Xa. Okay, Xa is equal to Na divided by Na plus Nb. Okay, next we'll go to yes, next one we have, just a minute. Okay, I have to explain here two more important concentration term, okay, that is your molarity, okay, and we have molality. These two I want to explain together because the terms are similar, so you may get confused. So there is a what else I'll teach you simultaneously, okay, so that you don't get confused here. Now what is molarity? Molarity is, I'll write just the formula because we don't want definition in the exam. Number of moles by volume of solution, please mark here, volume of solution into 100. Okay, and molarity is denoted by capital M and it is denoted by small m. So here it is number of moles by mass of solvent, by mass of solvent in kg into 1000, okay, into 1000. Okay, so this, if you are multiplying this 1000, this volume should be in ml and this mass should be in gram. Okay, then you have to multiply the 1000. If this is in liter, if I'll write down the formula here, so number of moles of solute by volume of solution, okay, it is in liter, then no need to multiply 1000. Similarly here, number of moles of solute by mass of solvent, okay, if it is in kg, then no need to multiply 1000. Clear this part? Next, which is very important, is suppose I am writing a term 2 molar solution. Okay, after the answer you get, that is 2 molar. Now what is the meaning of this 2 molar? It means 2 moles, suppose I write 2 molar glucose. So what does it mean? It means 2 moles of glucose, okay, 2 moles of glucose in 1 liter of solution. Clear? Now if I write 2 molar glucose, okay, that means 2 moles of glucose in 1 kg of solvent. Okay, 2 moles of glucose in 1 kg of solvent, 2 moles of glucose in 1 liter of solution. Okay, that is the difference between molarity and molality. That is the formula. Now further we can break this number of moles is equal to given mass by molar mass. Okay, given mass by molar mass. I hope this is clear. Okay, now moving to the next topic, that is your solubility. Okay, solubility is again of 2 types. One is solubility of solids in liquids and solubility of gas in liquids. So if you are talking about the first thing, that is solubility of solids in liquids, it depends, what is the 3 factors on which it depends: nature of the substance, temperature and pressure. Okay, so in nature what is there? It is something called as like dissolves like. That means polar solute will be dissolved in polar solvent, non-polar solute will be dissolved in non-polar solvent. Okay, that is, so for example, you can see salt and sugar are soluble in water because they are polar components. Naphthalene and anthracene, these are non-polar and will be soluble in non-polar solvents like benzene. Clear? Now coming to the temperature. So temperature, the solution process can be both exothermic and endothermic. Okay, it's not like it is always endothermic or always exothermic, but yes, if it is an endothermic process, then if you increase the temperature, the solution or the solubility will increase, and if it is an exothermic process, if you decrease the temperature, solubility will decrease. And then for the pressure, there is no effect of pressure on the solubility of solids in a liquid. Clear? So these are the 3 factors. Now moving to solubility of gas in a liquid. So we have 2 factors, that is pressure and temperature. Okay, so in pressure what happens generally, if you increase the pressure, solubility will increase. And about temperature, if you increase the temperature, solubility will decrease. This is for gas, this is fixed. Okay, so when we increase the pressure, solubility of the gas in the liquid will increase, and when you increase the temperature, solubility of the gas in the liquid will decrease. Now this is very common. Just imagine you have a container. Okay, just imagine you have a container, on that some gas molecules are there. Now if you compress it, if you give more pressure to that, then that gas will get inside the water and or inside the solvent, and it will get soluble. Right? Now when you increase the temperature, when you heat, now you have dissolved it. Okay, now if you start heating it, what will happen? These gas particles will get more energy, right? They can have more kinetic energy, and they can easily escape out from the solution. Right? So that is why when you increase the temperature, solubility will decrease. When you increase the pressure, solubility will increase. But now to measure, like how much I know if I give pressure it will increase, but with how much pressure, how much solubility will take place, that is governed by a law or by a rule, that is your Henry's law. Okay, so in that we'll talk about the effects of pressure. Okay, so now what does Henry's law tell? You don't have to go to this statement and everything. One very simple thing, Henry's law says that the more pressure you give, more will be the solubility. Okay, that what we have already studied. It is in the form of a law to make it more authentic, and it is also more convincing. Okay, so Henry's law is a gas law which states that at the amount of gas that is dissolved in a liquid is directly proportional to the partial pressure of the gas above the liquid when the temperature is kept constant. Okay, so now the formula of this one is this X gas or the mole fraction of the gas is represented as solubility. Okay, so we have used the concentration term mole fraction to represent solubility in this case. Okay, so this one is your solubility is proportional to partial pressure of the gas above the solution. Okay, and to remove that proportionality, we multiply a term, that is your Henry's constant. Okay, so P of the gas is equal to Kh into X of the gas, where P of the gas is the partial pressure of the gas, Kh is Henry's constant, X of the gas is the mole fraction of the gas. Okay, now you can see here, you can see this diagram is very relevant. So you can see that this is suppose the gaseous particles. Okay, so when you increase the pressure, okay, when you increase the pressure, number of particles that have dissolved has actually increased, right? This is because of the increase in pressure. Now let's see what is the next topic we have, applications of Henry's law. So we have three major applications. The first one is in the solubility of carbon dioxide in your soft drinks. Okay, so when we give very high pressure, the carbon dioxide get dissolved in that. So when you release the cap, okay, when you open the seal, you are releasing the pressure. So pressure is decreasing, solubility will decrease. So that is why we see the carbon dioxide gas coming out. Okay, next one is in the scuba divers. Okay, so scuba divers, when they go down, the pressure increases, solubility increases. So that is why what happens, the more amount of nitrogen they consume. Okay, so which can lead to a medical condition called as bends. Okay, to relieve that or to get rid of that, we use something called as, that is, the oxygen tanks of the scuba divers are filled with helium gases. Okay, I know when you do this scuba diving, you will actually feel it. The pressure is so high beneath the like ocean. Okay, on the ocean bed you can find the pressure, your ears will pain. Okay, you will find that pressure in your body. So if that gas, if more nitrogen you are consuming, and when you come out, right, actually the pressure is less. So that will what happen, the nitrogen solubility will also be less, and immediately the nitrogen will come out of the blood in the form of bubbles. Now these bubbles can lead to the blockage of the veins, and that is why you may experience something which is called as bend, a very severe painful experience. So to prevent that, the oxygen cylinders are mixed with which gas? Helium. This gas name is important, please remember. Next application is in the altitude, high altitude. So anoxia, what happens when we go high? Okay, atmospheric pressure is less means solubility will be less. So the oxygen that should be dissolved in our body or in our blood reduces. So our body gets less blood, less oxygen. So as a result of which our brain does not function properly, and that medical condition is called as anoxia. Okay, fine. Next we will go to the effect of temperature. Okay, so as I told you, see, pressure, we have two effects or two factors which affects the solubility of gas in a liquid. One is pressure, under which we studied the Henry's law. The second one is your temperature. Now what happens here, the KH value increase with the increase in temperature. Okay, so we have this formula, P is equal to K into X. I'll write like this, right? Now when you increase, so I can write also like this, K is equal to P by X. This X is nothing but solubility. Now see, when you increase the temperature, K value will increase. If K value is increasing, this value will decrease, right? So that is why mathematically you can say in this way that when temperature increases, K value increases, so solubility decreases. But what exactly happens is when you increase the temperature, the particles gain more kinetic energy to escape from the solution to the gaseous phase. Okay, now we have next thing that we are going to discuss today is your vapor pressure and ideal and non-ideal solutions. Okay, so what is actually vapor pressure, and vapor pressure in liquid solution, vapor pressure in solid liquid solution we will discuss. So before that, what is this vapor pressure term means? Now see, suppose you have a liquid, okay, in a closed container. So what will happen, this liquid will evaporate, right? When this liquid will evaporate, it will form gaseous phase here. Now since the container is closed, the gaseous particles will also get condensed to form liquid again, right? Two processes are happening. See, these liquid particles are going to the vapor phase. Okay, now you see this, if this container would have been opened, then the gaseous particles will move out. But here what will happen, since the container is closed, this gaseous particle will go, hit the container and then start condensing, right? You might have observed this when you heat something, when you put some hot water or something in a closed container, if you open the lid, you can find small droplets of water in that. That is because of condensation, right? Now what happens, see, suppose okay, now see, suppose you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 particles are there. So now what is the condition? You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm just thinking that these 2 particles are present in the gaseous phase and these 11 particles are present in the liquid phase. Okay, now after some time what happens? You will find more particles in the vapor phase, right? After that there is a equilibrium attained. Equilibrium attained means what? The number of particles in the vapor phase and the number of particles in the in the liquid phase remains constant. Okay, means I'll give a small example. See, suppose at this process was going on. Okay, so after a certain time, there was total 13, right? So after a certain time we found that 5 particles are here and I have 8 particles in the liquid phase. Okay, this is liquid phase and this is vapor phase. Understand it carefully. Many students think that when I am saying that the number of particles in gaseous phase and liquid phase remains constant, means they think that both will have same number of particles. No, both will have same number of particles. It may or may not happen, but means after certain you checked at this point of time. Now after 2-3 hours or after certain interval also, it will contain 5 particles also. This will only contain 8 particles. That number of particles in each phase will not change. Now why is that not happening? Is the process of evaporation and condensation has stopped? No, the rate of evaporation and the rate of condensation has actually become equal. What is that meaning? See, suppose now one particle went to the vapor phase. Okay, so here one particle formed vapor phase, that means this one is not there anymore. Okay, now when this one particle went to the vapor phase, at the same time this one particle came to the condensation, undergo condensation and came to the liquid phase. So this one came here. So what will happen? Okay, now you see 1, 2, 3, 4, 5, 1 to 8 is remaining. Again one particle will go, one particle will come down, one particle will go, one particle will come down. When this process is attained, when this, so it will be not there from the initial. You know what is equilibrium, right? After a certain time there is an equilibrium between the two phases. Okay, this equilibrium is established between the two phases after a certain time. After that what we have to do? At this point, when there is an equilibrium between the vapor and the liquid phase, at this point whatever particles are present here, they will exert a, whatever particles are present here, they will exert a pressure. Exert a pressure on this liquid surface. This, because of gas particles, there will be some pressure developed, and this pressure is called as vapor pressure. Okay, now let's see what happens. At equilibrium, the evaporation rate equals the condensation rate. Molecules in the vapor phase collide with the walls and lead of the container, causing the pressure. So this vapor pressure is due to what? These gas particles colliding with each other and due to the collision with the walls of the container. Next, evaporation and condensation occur at the liquid surface. So at this point, these two processes takes place. Increasing the temperature increases the rate of evaporation and increases the vapor pressure. Now if I increase the temperature here, okay, so what will happen? More number of particles will go. Okay, more particles will evaporate, so more number of gaseous particles will form, so the vapor pressure will also increase. Okay, so now what is this vapor pressure? We understood. Okay, the vapor pressure is the pressure created by the gas particles over the liquid solution when the system is at equilibrium. Now if I have in this container where I have taken two things, okay, it's a closed container, I have particles of A, okay, and I also have particles of B. Okay, now A will evaporate, okay, and B will also evaporate, right? So now when I have two liquids A and B, what is the total pressure here? So the total pressure here is due to the pressure of A and the pressure of B. This pressure of A is called as partial pressure of A. This is called as partial pressure of B. Total pressure is partial pressure of A plus partial pressure of B. Okay, so for a solution of volatile liquids means both A and B should be able to evaporate. Vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. So how much pressure A will be created, how much pressure will be created by A depends on the number of particles of A or the mole fraction of A. So I can say here that PA is proportional to XA, okay, and PA is equal to P naught A XA. Similarly, I can say that PB is proportional to XB and PB is equal to P naught B into XB. Okay. Now, if I see P total is equal to what? P naught A XA plus P naught B into XB. Okay. That is the Raoult's law or formula for the Raoult's law. Next, if I go to, this is the formula I have already discussed. Okay, here something I have to tell you. Okay, now if I want to calculate the mole fraction of A and B in the vapor phase, so I want to write YA and YB. Okay, what is YA? Mole fraction of A in vapor phase. Okay, XA is what? The mole fraction of A in the liquid phase. Now once they have gone to the vapor phase, okay, they both A and B has evaporated and there is a vapor pressure created. Then what is the pressure of A here? What is the pressure of B here in the vapor phase? So to that we have to calculate YA and YB, and it is equal to PA by P total, and this is equal to PB by P total. So if you remember, what is PA? P naught A XA by P total, and this is P naught B into XB by P total. Clear? Okay. Next we have something called as Dalton's law. So what is Dalton's law said? See that here I told you, no, this part. See, this part is Raoult's law. This part is Raoult's law. What? That the pressure of A here depends on the mole fraction of A in the liquid. But the total pressure is equal to PA plus PB. PT is equal to PA plus PB. Okay, that is pressure of A and pressure of B. That is, the total pressure is equal to A plus B. That is your Raoult's law. What is Raoult's law here? PA is equal to P naught A XA. This formula which we are deriving, this is your Raoult's law. This formula is your Dalton's law. Okay, I hope all of you have understood what is this one. Okay, next moving to, okay, now XA and XB can be written in any terms, right? You can write XA in terms of XB, you know, XA plus XB will be equal to 1. So you can change XA and XB and can derive it in any one term of the mole fraction. Okay, that is the derivation here. Now here you can see the graph. Okay, so if you have taken one component, it's P naught A, this is P naught B, and the total pressure will be equal to P1 plus P2. Okay. Next we have, yes, this I have already explained. Okay, vapor pressure in a solid and liquid solution. Okay, so now see, whenever you add any solute to a liquid, the vapor pressure will decrease. Remember this line, solute, a non-volatile solute is added to a liquid, the vapor pressure will decrease. What is the reason for that? Very simple. Now see, when we had any pure solvent, right, you see all these top particles were occupied by the solvent and they were evaporating. Now what happens if you added non-volatile solute, the surface particles are covered by the non-volatile solute. So now you see only 4 molecules can go to the vapor phase, whether there are more number of particles that can go to the vapor phase. So if less number of particles are in the vapor phase, less pressure will be created. So when less number of particles went to the vapor phase, less pressure will be created. So generally evaporation is a surface phenomenon. When you add solute, the surface is covered by all the some of the spaces are covered by the non-volatile particles, and that is why the pressure decreases. Okay, so this is done. Next, vapor pressure in solid liquid solution. Okay, so we have this one. Yeah, so the graph remains same, but here we have only one solvent. You see in the previous graph I have drawn 2 lines, but here it is only one graph because we have only one component which can evaporate. Okay, so you have PA is equal to proportional to XA, PA equal to P naught A XA. Clear? Now we have something ideal and non-ideal solutions. Okay, we'll discuss what is this one. Okay. Now, ideal solutions are those solutions which obeys the Raoult's law, and non-ideal solutions are those solutions which do not obey the Raoult's law. Now, again in non-ideal solution, we have 2 types of solution, positive deviation and negative deviation. And then we have something called as azeotropes as well. Let's see them in detail. Okay. So, first of all, ideal solution, it obeys Raoult's law. So, when I say that it obeys Raoult's law, what do you mean by that? So, I have 2 components A and B. Okay, and they both evaporated. Okay, I calculated with Raoult's law what should be the formula of the or what should be the value of the total vapor pressure here. Okay, just imagine this is the container. Okay, you have two components A and B. Okay, now here they created vapor pressure. You know the mole fraction of A, you calculate, you know everything, and you calculated using Raoult's law what should be the total vapor pressure here. Now you calculated and you measured the value. Okay, if both the values are coming same, that means it is obeying Raoult's law and it is an ideal solution. Okay, now if this value is not equal to the value which you calculated, then it is called a non-ideal solution. It can be more than the calculated value, it can be less than the calculated value. If it is more than the calculated value, we call it positive deviation. If it is less than the calculated value, we call it as negative deviation. Clear? So what is obeys Raoult's law, you understand? Obeys Raoult's law means I have taken two components A and B. I have calculated what should be the total pressure. I measured the pressure that is created. If the values are same, that means it obeys Raoult's law. Now if it is obey Raoult's law, then these properties will also be here. Delta H mix is equal to 0. So when you mix it, there is no enthalpy change. When you two solutions are there, right, two volumes you have mixed, their total volume, there is no change in the volume. That is also correct. Next, this is important here, AB interactions are equal to AA and BB interaction. So now see, when there was only A, there was only B. There was AA interaction, there was BB interaction. Now when you have mixed them, there will be AB interaction. So AA interaction, BB interaction and AB interactions, all of them are equal. Okay, so these type of solutions are called as ideal solution. Non-ideal solution does not obey Raoult's law. This is not equal to 0, this is not equal to 0. AB interactions and AA and BB are not equal. Okay, so now let us see about non-ideal solutions in detail. So non-ideal solutions are of two types, positive deviation and negative deviation. So first of all, very thing you should be knowing that you mixed two solvent or two liquids, volatile liquids A and B. You measured the pressure, you calculated the pressure. If the value of the pressure is more than the calculated value, then it is called positive deviation. If it is less, then it is called negative deviation. Now a question may arise, why is it not equal? Okay, so that is because the interactions between A and B. Okay, now suppose the interactions between A and B is very weak. Okay, A and B interactions are very weak, then what will happen? More amount of A, B will evaporate. Okay, so if more amount of A and B will evaporate, more pressure will be created, right? So that is why it exceeds the calculated value. Now when I am saying that AB interactions are less or weaker, so what is it? The AB interactions are weaker than AA and BB interactions. See, earlier it was having, earlier there were AA interactions, there were BB interactions. Okay, now when you mix them, okay, there is no AB interaction, now there is only AB interactions. Okay, only these interactions are there. Now if this interaction is very weak, right, then what will happen? A will evaporate, B will evaporate, all the particles will evaporate, more evaporation will take place, right? Because of that, what happens? The number of particles in the vapor phase will be more, vapor pressure will be more. Now if this AB interactions, okay, are more, now see, okay, now let us see the second condition where we have this AB interactions, okay, which is stronger, very strong interaction is there. Then what will happen? Very less amount of A and B will evaporate because they are very strong interactions. So less number of particles will be present here, less pressure will be there. So that is because of negative deviation. So you can see here, so if more number of particles will be there, more pressure will be there. So P total will be more than the Raoult's value, and here P total will be less than the Raoult's value because less number of particles are there. Next, delta H mix here will be positive, delta H mix here will be negative. Okay, so AB interactions I have already told you. Examples you can see here, ethanol and acetone. Now see, ethanol and acetone has no interactions. Ethanol was having very strong hydrogen bonding. Acetone will have very strong dipolar interactions. But when you mix them, there is no good interaction between these two particles, which is weaker than the original interactions they had. So now they will evaporate more easily, right? So if they evaporate more easily, more pressure will be created. Similarly, we have CH2 and acetone. Here what are the examples? Phenol and aniline, there is very strong bonding, hydrogen bonding is there. Chloroform and acetone is also an example of negative deviation. Now once this is done, we'll see the graph for this one. So this was the Raoult's law graph. Positive deviation means more vapor pressure will be created. So you can see the graph towards the up. And similarly here you can see negative deviation, there is a decrease in the vapor pressure. So the vapor pressure will decrease. Okay, fine. Now we have something called as azeotropes. So what is exactly azeotropes? Now azeotropes is a special type of solution, special type of binary solution, means two components are there, and these two components, they have some individual boiling point, individual melting point, but when you mix them at a certain proportion, they form azeotropes, means the solution will boil at only one temperature. Okay, when you boil it, both will boil at the same temperature, so you cannot separate them out. This is called as azeotropic mixtures. Okay, now azeotropic mixtures have there are again two types of azeotropic mixture. One is minimum boiling azeotrope and maximum boiling azeotrope. Now what is minimum boiling azeotrope? Suppose A and B was there. Okay, A's boiling point was 100 degree, B was 120 degree. Now when you have mixed A and B, their boiling point will be less than the boiling point of both the components. Okay, it will be somewhere around 70 degree, less than the boiling point of both the components. Minimum boiling azeotrope. Now maximum boiling azeotrope means 100 and 120 was there, the mixture boiling point will be more than both the boiling points. Okay, it will be 140. That is called maximum boiling azeotrope. Now when do we find minimum boiling azeotrope? Okay, see, so when we have maximum boiling azeotrope, means they are boiling at a very high temperature at this point. Earlier they were having some different boiling point, but when you mix them, they are boiling at a very high temperature. That means what? Their interaction is very strong. If interaction is strong, then it is which type of deviation? It shows negative deviation, right? So for maximum boiling azeotrope, it shows negative deviation. Similarly, minimum boiling azeotrope means it is boiling very easily. It is boiling very easily means that A and B have weak interactions, and if it is weak interactions, it is positive deviation. So that is why shows positive deviation. Examples of maximum boiling azeotrope is nitric acid and water at this concentration, and here you have ethanol and water. Okay. Next, we will move to some questions here. The azeotropic mixture of water and ethanol boils at 78.15 degrees Celsius. When this mixture is distilled, it is possible to obtain pure H2O, pure C2H5OH, pure H2O as well as pure C2H5OH, neither of them. So you see now they are boiling at the same temperature, right? You cannot separate them. So it is not possible to obtain either of them in the pure form. Now solution A contains acetone dissolved in chloroform. Okay, solution A have acetone plus chloroform. Okay, acetone dissolved in chloroform. Next, solution B contains acetone dissolved in carbon dioxide. Acetone dissolved in carbon disulfide. The type of deviation from Raoult's law shown by solution A and B are respectively. So here what happens? There is more interactions here, right? So if it is more interaction, we get a positive deviation here. So that will be positive. So I can eliminate these two options. Now talking about CH3, COCH3 and CS2. So if you see the examples that I have given you, one second, let me show you where it is. Yes, CS2 and acetone, right? This will show positive deviation. Okay. Oh, just a minute. Okay, fine. I did a mistake, I think here. Just a minute. Okay, just a minute. Here I have done a small mistake. Yes. Now here there is very strong interaction, right? Very strong interaction means it will show negative deviation. Okay, so very strong interaction means this first one will be negative deviation, and here there is no such interaction or the weaker interaction, so it will show positive deviation. The correct answer here is option number D. Okay, fine. Next we'll go to, for an ideal binary mixture, what are the conditions given? So you should know for any mixture delta G is always negative. Okay, so we can eliminate these two options. Delta G has to be negative, this option is correct, and delta S mix has to be greater than 0, so option number D is equal to correct answer. Okay, Next we have the colligative properties, very important. So we have 4 colligative properties, right? So we all know that. Let's see quickly. So colligative properties are those properties where the properties of the solutions depends on the colligative properties. Okay, so now suppose you have relative lowering of vapor pressure. Okay, now what is this relative lowering of vapor pressure? So when you add a solute to the solution, the vapor pressure decreases. How do we calculate that? Delta P by P naught. Okay, delta B by P naught is equal to XB. Okay, so what is P naught? P naught is the actual pressure of the solvent. P is the pressure of the solvent after adding solute. Okay, so what is here P naught? P naught is actual, or I can say original pressure of the solvent. Okay, P naught. Similarly, P is the pressure of the solvent, after adding solute. ठीक है, so that is P naught minus P by P naught is equal to the mole fraction of the solute. So you can see this property depends on the number of moles of the solute. So it is depending on the amount of solute added. So that is why this is a colligative property. Okay, now you can see here generally when we do calculations, especially in this type of question, this NB can be ignored because in a large amount of solvent very few particles of solute is there, so we can generally ignore it. Okay, let us see the next one question on this topic. The vapor pressure of water in the solution is 50 in the 50 gram of urea dissolved in 850 gram of water is. Now vapor pressure of pure water is given. Now when vapor pressure of pure water is given, that means what? P naught value is given to you, which is 23.8 mm of Hg. Now after adding urea, we know the pressure will decrease. What is the new pressure of this solution? That is what we have to calculate. Okay, so I have to calculate this P value. Clear? Now we have something, number of moles of urea here, that is your given mass by molar mass. So 50 by 60, so it is 5 by 6. Number of moles of water, okay, so that is your 850 gram divided by 18. Okay, now if I want to calculate the mole fraction of urea, so it is 50 by 60. Let me write down the formula first. Mole fraction of urea will be what? Number of moles of urea by number of moles of water. So number of moles of urea is 5 by 6. Okay, number of moles of water is 850 into 18. Okay, so let me just calculate this one. 6 ones are 6 threes are 18, right? Yes, so I can cancel here also. 5 ones are 5 90s are, right? So 3 by 190 I got. Okay, this is the number of mole fraction of urea. So let me just write down the final answer. Mole fraction of urea is 3 by 190. Right, you remember, I'll just show you the calculation once again. 50 by 60 divided by 850 by 18. So I got 18 by 850. Let us see the next question here. The vapor pressure of water in the solution having 50 gram of urea dissolved in 850 gram of water is. The vapor pressure of pure water is 23.8 mm Hg. Okay, so now let us see that the vapor pressure of pure water is given to you. Okay, this is already given. We have to calculate the pressure of the water when there is solute added to it, right? After addition of solute, the vapor pressure will decrease. So what is that new pressure after addition of solute? That is what we have to calculate. Now let us see first the number of moles of urea. That is what? Given mass by molar mass. So 50 gram by 60 gram, or I can just simply write 5 by 6 here. And what is the number of moles of water? Given mass by molar mass 850 by 18. Okay, now if I want to calculate the mole fraction of urea, it is equal to number of moles of urea by number of moles of water. I told you if there is a big solvent, we can generally eliminate the number of moles of urea in this formula. So what I will get here, 5 by 6 divided by 850 by 18, and if I just multiply it, it will become 18 by 850. Okay, now if I just want to calculate this one, let me see, 5 by 6 divided by 850 by 18, so it becomes 18 by 850. Yes, so now if I just calculate, it is 6 ones are 6 threes are and 5 ones are 5 190s are, so I have 3 by 190. Okay, this is the mole fraction. Now let us do the formula. What is our formula? Delta P by P naught, or I can say 23.8 minus x by 23.8 is equal to 3 by 190. Okay, so what is here given? Just we have to solve this. So I can 23.8, I'll just calculate as 24. Okay, so you can see the options are very far away from each other. And one more thing also I'll be telling you, so vapor pressure will decrease. Okay, so the vapor pressure cannot increase, so definitely we can eliminate these two options. Now here you see the vapor pressure has decreased drastically, means it has almost become half, 23 to 12. Okay, that much decrease also does not take place, a slight decrease takes place. So I think the correct answer will be option number A. By seeing the options you can easily guess the answer, but let me solve it. Okay, so if I just take this one as 24, okay, 24 minus x by 24 by 3 by 190. Okay, so what I can do here is I can calculate it as 3 into 24, and this 190 I'll make it 200 for just calculation. Okay, is equal to 24 minus x. I'm just doing a rough calculation. Okay, so how much I'll get? I can take it like x, I can solve this side, so x will be equal to 24 minus 3 into 24 by 200. Okay, so how much we are getting? So I can see like 24 into 2 is 4800 minus 3 into 24 is 72 divided by 200. So 4800 something by 2, it will come 20 point something only, it will come, right? You can easily see 4800, you just subtracted 72, means you can say something around 80 or something, 70 you subtracted, and then you are dividing something with this 200, so it will come to 23 point something. So the correct answer has to be option number A. Easily you can guess the answer, you do not have to solve this much question. Next we'll go to elevation in boiling point. So whenever you add any solute, the boiling point increases, and the formula is delta Tb is equal to Kb into m, where Kb is your molar elevation constant, m is the molality. Okay, all of you might be knowing the formula here. So here we have a small question. The elevation in boiling point was 0.52 degrees Celsius when 6 gram of a compound X was dissolved in 100 gram of water. The molecular weight of X is. Okay, so elevation, we have this formula, right? Delta Tb is equal to Kb into m. So what is this delta Tb value? 0.52. Don't have to convert it into Kelvin. Okay, this is a difference. Difference remains same whether it is in Kelvin or Celsius. Then I have Kb value. Kb is 0.52 again. You can see how the numbers are given so that we can easily cancel. Molality, given mass, molar mass I have to calculate into 1000 by mass of the solvent is 100. Okay, so we can just cancel this one, take this m this side, so I will get how much? 60 gram, option number B here. Okay, very simple. Next, depression in freezing point, delta Tf is equal to Kf into m. Kf is your molar depression constant and m is your molality function. Okay, now similarly you can see a question here, the molality of a solution containing a certain solute if there is a freezing point depression of 0.184 is. You have to calculate the molality. So we have this formula, right? Delta Tf is equal to Kf into m. Now delta Tf value is given to me as 0.184, Ka value is 18.4, okay, into m. So what is m value? Okay, 184 by 1000. Okay, then I divide it by 18.4, it is 10. Okay, so now how will I get? We can do it like yes, I divided it. Okay, so now if I just cancel this one, I will get 10 to the power of minus 2, that is your 0.01, right? Okay, next question number, that is your osmotic pressure. So what is osmotic pressure? The pressure that stops the flow of the solvent is called as osmotic pressure of the solution. Now let me explain. See, whenever suppose you have a solution, okay, A here and B here, and you divide with a partition. Okay, now A is a, I'll say, less concentrated, okay, and this is more concentrated. That means what? Here there is less number of solute, okay, and here there are more number of solute. Okay, now what will happen? The water will flow from here to here, okay, or water or the solvent will flow from less concentrated part to the higher concentration part, and that is called as osmotic pressure. Now the formula of this osmotic pressure, pi is equal to CRT, okay, C is your molarity, R is the gas constant, and T is your temperature. Clear? Then R value has to be, okay, let me tell you the R value. R value here is generally 0.0831 liter ATM, mole inverse and Kelvin inverse. Okay. Next we have two solutions having the same osmotic pressure is called as isotonic solution. This is also a very important term used in the osmotic pressure concept. Then what happens? Now see, so I told you that, okay, once again, see here I told you that when you give osmotic, this is osmosis. Now if I give a pressure here, okay, I put some pressure here to stop this osmosis, that is called as your osmotic pressure. But if I give more than the pressure, like suppose the osmotic pressure is 5 Newton, if I give more pressure 6 Newton, then what will happen? Water will start flowing from this side. Okay, you are keep pushing this, right? When you push more water will start flowing from this side to this side. That is called as reverse osmosis, and reverse osmosis is used widely in your desalination of water. Next, isotonic solutions have the same osmotic pressure, very important term actually. Next, something called as abnormal molar mass. Now abnormal molar mass takes place when you have the solute, okay, the solute that we are adding, if it is associating or dissociating, then we have something called as abnormal molar mass. Okay, now this abnormal molar mass is corrected by something called as Van 't Hoff factor. And how do we calculate the Van 't Hoff factor? You have three formulas, and the most common formula that we used is the number of particles after dissociation or association divided by the number of particles before association or dissociation. Okay, so what happens? Suppose you have taken NaCl, it will dissociate to give you Na plus and Cl minus. So one particle you dissolve, but in the water it became two particles. So what is the Van 't Hoff factor? Number of particles after dissociation 2 divided by the number of particles before dissociation 1. So 2 by 1. Okay, so generally dissociation is we'll do dealing more questions with dissociation, but association is also there. Now if there is dissociation and association, there can be 100% dissociation or certain amount of dissociation. It's not like a complete dissociation doesn't take place sometimes as well. Okay, so in that case we calculate the extent of dissociation, the extent of association. So to calculate the extent of dissociation, the alpha is equal to I minus 1 divided by n minus 1, where I is your Van 't Hoff factor, n is the number of particles. Okay, similarly alpha is equal to I minus 1 by 1 by n minus 1. Okay. Okay, now we'll see a question here. Which of the following colligative properties can provide molar mass of proteins, polymers and colloids with greater precision? So this is also osmotic pressure application, you should be knowing. It is used to calculate the molecular masses of macromolecules. Okay. Okay, next, which of the following aqueous solution have the highest boiling point? So we know the boiling point is delta TB is equal to KB into M. But yes, here what happens, here something I have to introduce, that when the solute is there which associates or dissociates, the colligative property is also written like this. Now delta P by P naught is equal to I into XB. Okay, this I factor is considered. Similarly, delta TB is equal to I into KB into M. Next we have delta TF is equal to I into KF into M. Okay, next I have osmotic pressure, I into C into R into T. Clear? Okay, now moving forward, yes. Okay, so where the highest boiling point is there. Okay, so I value is there. Okay, now I value you have to calculate. For NaOH the I value is 2 for option number A. For option number B it is Na2SO4 3. For option number C it is NH4NO3 2. It will dissociate like this, NH4 plus and NO3 minus. For option number D also it is 2. So now you see option number B, 3 has the maximum number of ions produced, maximum elevation in boiling point will take place. So option number B is the correct answer. Next we have a homework question for all of you. If 3 gram of glucose is dissolved in 60 gram of water at 15 degrees Celsius, the osmotic pressure of the solution will be. Okay, so this is a homework question. You all have to try this question and put down your answers in the comment section. Okay, so that's all students. I hope that this one short lecture will help you to revise all the concepts quickly and note down all the formulas and practice some questions. Do not worry, I'll be coming up with a detailed question solving session for this chapter as well. So in my next live class, that is on Friday, okay, on Friday we will be having the numericals or questions from the chapter biomolecules and solutions. Okay, so yes, let's get started and please get let's get ready, revise these 2 chapters and come Friday morning at 11 AM where we will be solving the questions. Okay, so that's all students, and see you soon in the next class. And please work hard. This last days of the exam are very critical. Do not waste a single time also. Please study hard. Any doubt, any clarification, any help you required, please do put in the comment section. We will definitely help you. Okay, thank you so much.